movement to surface waters look like in grazing systems, how that might be a little bit different than our annual cropping systems. And then maybe give you some tools to talk to consumers about your different water quality practices, or maybe give some strategies of how to tweak your system to really maximize water quality benefit. So we'll kind of first set the stage by talking about Wisconsin's grand water quality challenges. And the first one we'll talk about is kind of sediment itself. So sediment can impact our surface waters in a couple ways. And one of the big ones is habitat degradation. So when we have sediment entering our waters, it can kind of impact the clarity of our water. And this can do a lot of different things, one of which is blocking sunlight from getting to those aquatic plants. It can also impact some of our visual predators like largemouth bass and brook trout. And when that sediment eventually falls, it can muddy up those kind of surface and stream beds we see right there, which are really important habitats for our macroinvertebrates and mussels and all sorts of other cool insects. So what we were talking about earlier today, it's really important to kind of increase diversity on our pasture systems, but also when we're keeping sediment on the landscape, we can be impacting biodiversity and other ecosystems too, which is pretty neat. So the next one we'll talk about is phosphorus. So phosphorus is considered Wisconsin's #1 water quality pollutant because it's the reason the majority of our surface waters in Wisconsin are listed as impaired by the DNR. So over here on the right, that's kind of cyanobacteria. And what happens is when we get excessive phosphorus into our aquatic ecosystems, the cyanobacteria is naturally occurring, but when we get that influx of phosphorus, the cyanobacteria are really like this, and they kind of form these really big blooms, which sometimes will form these harmful algal blooms we see on the left. So kind of a misnomer that it's called algae, but it's caused by bacteria. And these cyanobacteria can produce cyanotoxins, which is what can cause like skin irritation in humans, or sometimes what dogs drink and it makes them sick. So if you're ever at surface waters and see kind of the no swimming signs, this is likely the reason why you're seeing that. And then the third one, and then in extreme cases too, when microbes in the system start to break down these harmful algal blooms, they'll use up a lot of the oxygen. So that's why in kind of extreme cases, we might see some of those fish kills that you might hear about in the news and things like that. The third one we'll talk about today is nitrogen. And nitrogen can be a surface water contaminant. So it can kind of contribute to the toxicity of harmful algal blooms and also eutrophication, which is often what we see examples of in the Gulf hypoxic zone. But when we're thinking about it in the Wisconsin context, we normally think of nitrogen as a groundwater issue. And this is because nitrate, so that NO3 negative, this is a plant available form of nitrogen. So it's readily taken up by plants, but it doesn't really bind well to our soil because most of our soil is negatively charged. So it's readily moving through that soil profile, and if it's not taken up by our plant roots, it can leach below the root zone and get into our groundwater. In Wisconsin, this can really be a problem because our groundwater is our main source of drinking water. And when we have excessive nitrates in our drinking water, this kind of impacts humans' red blood cells' ability to hold on to oxygen. So this can be really a problem in infants and also pregnant women. So I should have introduced myself, but I work for Extension and I work for the Agriculture Water Quality Program. And this is Extension's newest program that was really created in response to these water quality challenges. And our program is unique that it's specifically looking at how agricultural production practices impact water quality. So we kind of look at when nutrient losses happen in cropping systems, why they happen, and really kind of what practices on the landscape we can do to kind of minimize these impacts. And one of the ways we do that is working with a lot of university researchers or around the country. But nested within our program is the Wisconsin Discovery Farms, which I don't know if most of you have heard of it. They have primarily done mainly annual cropping studies, but they have done some grazing studies, and we'll be talking about them today. So I thought it would just be relevant to talk a little bit about them. So this is a farmer-led research group, and that's part of UW Extension. And what's unique about this is that prior to this group starting in the early 2000s, a lot of water quality research was kind of happening on that small plot scale or on research farms or maybe in the lab, so it wasn't really representative of what was happening on the true farm landscapes when we're thinking about topography and different soil types and all the complexities. So this has been happening for about 20 years, and people really like the idea, so now it's in Minnesota and Arkansas and Vermont. And we now have one of the most robust water quality databases kind of in the whole country, which is awesome. And admittedly, we don't have a lot of sites in the Northwest, so they've kind of been in other counties throughout the state, but the program is strong and up and going. And so this will be some of the data I'll be presenting on today. And really their focus has been on edge of fields water quality monitoring, tile line monitoring, and recently lysimeters, which looks at nitrate leaching below kind of the root zone. That's kind of the newest iteration of what they're doing. So because I'll be talking about some of that research today, I want to talk a little bit about the how edge of field water quality research actually happens and what that looks like. So this is what an edge of field monitoring site looks like. So we have these wing walls and berms that direct all of the natural surface flow from a defined area, normally like edge of field on a farm, and it flows through an H flume. And then it gets sent up to that gauge house and collected in all this 24-hour refrigerated sampler, and then those samples are taken to the lab and analyzed. And what's really unique about this is these sites are on the edge of field year-round, so they can capture a lot of our really important nutrient loss times that are super relevant to Wisconsin. And I think a lot of the, when we look at data from other states, it's not always applicable to us because they don't have our cold climates, our frozen soils, kind of all the unique things about Wisconsin, unless sometimes when we look at Canadian research. So these monitoring sites are also in place for 5 to 7 years. And this really helps us get an accurate picture of nutrient loss on the landscape, because we know, some years like this where it was super droughty, or you might have really rainy years. So that 5 to 7 year period helps us see the variability between years and helps us kind of get a better picture of what's happening on the landscape. And those H flumes are equipped with this nice heat tape, so then there's not ice buildup, and so we can get that, capture the flow. So what do these sites measure? They look at total surface runoff, and then they're also analyzed for nutrients, including suspended sediment, nitrogen, phosphorus, pH. These also help us assess the timing of losses. So this is one of our newer sites that's in Marathon County, and it's looking at a custom dairy heifer raising site. But this is kind of in its first year, so we don't have a whole bunch of data from that. And these sites are really unique too because they help us look at loading, which is total amount of nutrients lost per year, which if you're ever looking at the research, this is in pounds per acre. And this kind of differs from other types of water quality monitoring, like concentrations, which are really looking at or stream sampling, looking at concentrations, which are really a snapshot in time. And these are typically in milligrams per liter. So if you think about stream sampling, if you go out and you're sampling after a really big runoff event, you might be getting a really concentrated reading, and this might not actually be accurate of kind of the nutrients in that stream year round. Or if you're sampling when the stream is really high, that sample could be diluted. So again, not really getting a good picture of maybe the land use around that stream. The other thing about stream sampling, if we think about how water flows, the water in the stream could be coming from your farm and your neighbor's farm, and maybe it's near a factory, or maybe it's near some other site or some homeowners. And so you're not really accurately able to say, you did this to the stream or you did this. You can't really draw those conclusions. But with the edge of field monitoring, they're from defined watersheds, so we know where all of that water is coming from. So we can definitively say what you did on the landscape had this impact on surface water quality. So this methodology really helps us to verify conservation practices, see how they work, what doesn't work, how that changes under different climate conditions, kind of all the things. And then I just put this in because this is kind of Discovery Farm's newest thing, and I know Nick used this term earlier, but this is kind of like the Cadillac of nitrate leaching equipment. So this measures nitrate leaching below the root zone. So what they do to install these is they take an undisturbed soil profile and they dig really deep and they kind of carve out the side and then stick the box underneath. So theoretically the nitrate or the water is moving through a natural soil profile, and it's not using any vacuums to draw that water down or anything, so it's kind of the natural flow of water movement in that system. I mean, hopefully if everything's set up right. And because this is capturing all of the water in that system, they're also able to calculate loading, so you could see true amounts of nitrogen that is being lost from that field below the root zone, so theoretically what could be getting into groundwater. We don't have any of these under pasture sites yet, so again, kind of also the reason wasn't going to talk as much about water quality or groundwater quality today because we just don't have as much research on it yet. But just wanted to tell you a little bit about the technology if you kind of ever see it in the future, people talk about it, because there's a lot of different kinds of these lysimeter technologies. So now that we've talked a little bit about how water quality research is done, especially from an agriculture standpoint, now we'll kind of switch gears and talk about the relationship between grazing and pasture systems and water quality. And grazing and pasture systems can have a lot of protective benefits for water quality, but this relationship is not automatic. There's a lot of mediating factors like stand type, biomass, timing, duration of rotation. And don't get super overwhelmed by that list or anything. We'll be going through most of those today. But really the point here is that in any natural or agricultural system, it's not perfectly closed. So some nutrient loss is inevitable, but really our goal here is how do we make the system less leaky? And really to do that, we have to understand how nutrients move to surface water quality. And because we know phosphorus is really our major surface water quality pollutant, we have to understand how phosphorus moves. And once we do that, then we can know how to manage for it. So if you've ever looked at the phosphorus cycle, in your life or jobs or school, you'll know that it's really complicated. So for the sake of today's presentation, I created just this really simple graphic we'll be referring back to. And the main points here is that for water quality impacts to happen in grazing systems, there has to be both a source of those nutrients and a transport mechanism like rain or snow. And I think historically we spent a lot of time talking about that transport or that runoff piece and maybe not enough about managing for source. So we're going to spend a lot of time talking about that today. So the first piece we'll talk about is the pasture plants themselves. And so, when pasture plants die and decompose, they can release a little bit of phosphorus into the system. They can also release phosphorus through our freeze and thaw cycles. So especially here in Wisconsin, these ice crystals can form, and this can cause cells to burst or lyse and release some of their innards, which has phosphorus in it. And this is kind of dependent on the species. So brassicas, like turnips and radishes, tend to release a little bit more than grasses and legumes. And this is kind of an emerging field of research. But they think that perennial species are evolved to better resist these frosts and survive winters, so they release a little bit less phosphorus. So many of your perennial systems that a lot of you have, you're probably already doing a great job of this, and this might have more implications for our cover croppers. And generally, this is a pretty low contribution compared to other sources, but just one to be mindful of. But one of the things we really can manage for in terms of our pasture plants is managing for appropriate stand height to maximize erosion control. So it's often helpful to think about above ground biomass as kind of a mirror to what's happening below ground. So when plants are consistently overgrazed, this can take up the carbohydrate stores and physically shrink the root systems, affecting the above ground biomass as well. And we know this is really important in terms of erosion because those root systems physically hold onto that soil, preventing it from getting into runoff. And that above ground biomass can also intercept raindrop, which they've done some studies that the physical force of a raindrop hitting the soil can detach those soil particles and they can get into runoff. So when we have this really good canopy cover, we can be doing a really good job of controlling this erosion. So to managing for appropriate stand height is obviously species dependent, and I'm going to use that terminology, take half, leave half. I know that's not always possible, but when you can. So they typically say grazing to about 4 to 6 inches can really maximize regrowth and resilience of that pasture, and we can really get some good erosion control benefits with this. I have this video that I know is not going to work, but if anybody Googles this on their own time, University of Kentucky has this really cool time-lapse video, and just the The sample on the right that was only grazed down to 3.5 inches, you can just see how quickly it rebounds. And while it's not showing the roots in this video, it's just a really good illustration of kind of how fast that root can rebound and with that strong above ground canopy and root system. So from that Discovery Farms water quality monitoring I was talking about before, we do actually have really good evidence to validate these benefits. So on the x-axis here, we're looking at different systems, so like alfalfa, grass, corn compared to pasture. And again, we don't have as many pasture samples, but we have a whole bunch of annual cropping systems to compare to. And on our vertical axis, we have soil loss in pounds per acre. And what you'll see in our pasture systems is that when we're managing for that good stand height, we're doing a really good job of controlling for that soil loss, especially when we compare that to other systems like corn silage, which are harvested really early, and especially if we don't have cover crops in those systems, we're leaving that soil bare and vulnerable for a pretty extended amount of time and can get pretty high losses. Losses we've seen from the research are sometimes up to 50,000 pounds, so it's a whole lot of soil. And when you're controlling for that sediment, you're also doing a really good job of controlling for your particulate phosphorus losses, or the portion of phosphorus that is bound to soil particles. So this graph basically mirrors what we saw in the last graph, but on the vertical axis, we have particulate P in pounds per acre. And again, when we're controlling that soil, doing a really good job of controlling that particulate phosphorus compared to some of our other systems. So the next source of phosphorus in a grazing system is the manure from animals, which we know can be both a rich source of nitrogen and phosphorus. So really to minimize water quality impacts, it's really important to distribute that fertility using rotationally grazing, being mindful of that stocking density. We also know that animals tend to congregate around bales, waters, and minerals. So really important to rotate those around too when you can to kind of promote uptake from plants of that manure. And I also put shade on this list because while you can't physically pick up and move a tree, or maybe you can with some of the shade structures that Nick was talking about earlier. But you might be able to get creative with your grazing system, kind of putting waterers on the opposite side of trees to really homogenize that manure cover on your paddocks and kind of reduce losses. So the next source of phosphorus in a grazing system is the soil itself. And I think sometimes that this can be a really underlooked source of phosphorus. And this is because and sorry to any of the soil scientists out here, this is going to be like a way oversimplification, but our soil can be a really, really big pool of phosphorus. So total soil phosphorus ranges from 200 to 6,000 pounds per acre, but we often don't hear about this a lot because 90% of it is not available to plants and not really what would be tested with our normal agronomic samples. But a lot of this phosphorus is tied up in some of our organic matter, or it might also be sorbed to soil particles like clay. But you'll see from all the bidirectional arrows on this graph that, so only that dissolved P is what would be available to the plant and also available to be lost. But you'll see from all these arrows that the phosphorus is always in flux in the soil system. So from different processes like microbes breaking down soil organic matter, or maybe some changes in the soil chemistry, some phosphorus will come desorbed from those clay particles and get into our soil solution, which can be taken up by the plant. And so these kind of all happen at different rates. So a lot of people like to use the analogy as soil phosphorus as a bank account. So some of those sources might be more in our like long-term savings and are really slow to be released, and others maybe are more like a checking account and by different processes will become released. But my main point here is that really the bigger this soil phosphorus bank account is, the more it can be potentially contributing to losses. So really what do you do if you have soils that are testing very high in phosphorus that you suspect might be contributing to these losses? This would be a time to really consider some phosphorus drawdown strategies. So this includes reducing manure inputs on high soil test phosphorus fields in conjunction with focusing hay harvest on these fields. And if at all possible, especially if they're testing really high, trying to sell that off farm to really help with some of that phosphorus nutrient exports off farm. Another approach, which might not work for everybody because it kind of depends on the infrastructure but is partnering with another farmer to graze their cover crops and or corn stover. So this can be kind of a win-win situation to get that fertility where it's needed. It also might be able to save you a little bit of money because while you might not get great yields with rye after corn silage, you could extend the grazing season a little bit, and anytime you're not feeding hay, this can be an opportunity to save some money. So opportunities for this could exist after those early harvested crops. So I have corn silage in this picture, but maybe also after wheat. But it is important to really be realistic with this because phosphorus drawdown, because of those pools we were talking about earlier, is really, really slow. So even if you want to draw down your soils, it might take a really long time. So for example, a typical corn crop is only taking out about 3 to 5 parts per million of phosphorus per year. So the next one we'll talk about is mineral, which I'm a little scared to talk about because I am also not a nutritionist. So someone might have more information about this in the audience, but just talking about some of the more the phosphorus implications here. So phosphorus is an essential macronutrient for animals, but when it is supplemented beyond an animal's need, it increases in the manure, and this is kind of an environmental and economic concern because phosphorus is one of the most expensive nutrients to feed, and then also when those rates increase in manure, they could also be at risk for losses. The good news is that generally Wisconsin's forage does provide adequate amounts of phosphorus. They did some pretty extensive sampling in the Chesapeake Bay area and found that 70% of their samples were meeting cattle's nutritional need kind of at that peak time, peak lactation, and then 99% of samples were meeting it at all other life stages. And there was some Wisconsin research too in Holstein steers, and when they were supplementing phosphorus kind of above the Holstein steer's need, it didn't lead to any additional weight gain. So kind of no real benefits to supplementing phosphorus beyond what an animal needs. So soil test levels can be a fair indicator of the amount of phosphorus that you have in your forage, but really to get an accurate picture, you want to test that fresh forage, and also be sure to test hay too, because depending on the maturity of the plant, they can have different phosphorus levels, and you really want to make sure that your animal's need is being met all year. If these peer requirements are met, consider choosing mineral low or zero on phosphorus. Or if you're using a custom mineral mix, it might just be a good time to check in with your supplier to see if there's phosphorus in there. So it might be able to save a little bit of money and also kind of reduce some of that phosphorus source in your system. So the next one we'll kind of pivot and talk about transport. And transport is difficult because we can't control the weather, but we can identify when vulnerable times of the year are and manage accordingly. So every year is going to be a little bit different, but when we look at the research, this general trend really does emerge that the majority of runoff losses happen during our non-growing seasons and pasture systems. So this graph is from some water quality edge of field monitoring in southwest Wisconsin, and the top graph is looking at precipitation, and the bottom graph is looking at runoff, and then we kind of have the dates on that bottom graph. And what it shows us is that even though precipitation is peaking during that summer time period, our runoff is peaking in those winter and kind of early spring March months. And the reason we likely see this kind of in those March and early spring months is maybe we have a little bit of frozen soil. The plants aren't growing, so they're not evapotranspirating that water. And if we're getting back-to-back rains and our soil is getting saturated, there's nowhere for the water to go, it's going to run off. And then in the winter, in January and February, especially up here, we're almost always dealing with our frozen soil conditions. And especially if we get that concrete frost at the surface. So this is when all of the water in soil pores is frozen, and they call it concrete frost because it essentially forms concrete and is creating really right conditions for runoff. So we know that early spring and winter are super vulnerable times, which is actually, we see the same thing in annual cropping systems too. But what we can do is we know when those vulnerable times are, so it's really important to identify and avoid grazing hydrologically sensitive areas. So this would include fencing off cattle or animals that you're grazing from riparian areas and streams, keeping them out of concentrated flow areas, especially when we're going to get those heavy rains or spring melts that we're seeing in the center. This might also help to ease some compaction issues because we know that when animals have access to wet soils, the treading and hugging can really lead to some increased runoff that we tend to see in some of the data in our graze systems compared to other systems. But ultimately, really, you know your land best, so you want to pay attention to where water is flowing after large storm events or in that spring snowmelt period to kind of identify where these hydrologically sensitive areas are. So from the grazing research we were looking at before, we know that when we're managing for stand height and we have good pasture coverage, we're doing a really good job of controlling that particulate phosphorus or the portion of phosphorus that is attached to soil particles. What about phosphorus that's dissolved in water? So, and I always like to just toss in this graphic because even if you have clear runoff running off your fields, because we know that some runoff is inevitable, but even if it's clear, you could still be losing nutrients. But the grazing research from Wisconsin tells us that 80% of phosphorus losses are in the dissolved form, which again makes sense because we know we're doing a good job of holding on to that soil. The majority of these losses happen during the winter and non-growing season, and this is concerning because the monitored dissolved phosphorus concentrations in a lot of the grazing research is often above water quality eutrophication levels. So we likely see this in areas where high transport and high source conditions really overlap. And this is really common to see in our outwintering areas. And this is because we're kind of combining those tricky transport conditions like frozen or wet soils, which might lead to some increased compaction and increased runoff. And when we pair that with high phosphorus sources like less frequent or no rotation, which is often the case in outwintering areas, and concentrated manure and urine deposits, you might get some soil test phosphorus buildup, especially if we're not rotating those areas from year to year. And in these areas, we are also using hay, and especially if we're importing that hay from other farms, we could be adding additional phosphorus into the system. So this is really great in theory, but what does it actually look like on a farm? So now we'll take a case study of an outwintering area from the Discovery Farms data. So this one was looking at I'll draw your attention to the K5, K6 pastures. So K5 was looking at surface runoff, and then K6 was looking at tile line monitoring, but they were from the same area that was primarily used in the winter during our frozen soils or frozen soil conditions. So we know we have tricky transport conditions. We also have pretty high source conditions. So these are soil test levels just from that K5, K6 area. And these were sampled for 3 years during the monitoring period from that 0 to 6 inches, which is pretty typical for your standard agronomic soil sample. And we have soil test numbers in the right. And we can see that these are all pretty high in that excessively high category from UW recommendations, anything above 42 parts per million. And that's for lower organic soils, so this is actually a more kind of conservative number. But we can see all of those numbers were kind of far above that, so this was a tricky source area as well. And then kind of even more troubling when we look at that 0 to 2 inches, which is at the surface. These are sometimes almost double what we were seeing in those 0 to 6 inch samples. And this is troubling from a water quality perspective because we know that the surface of the soil is really what's most likely to be interacting with runoff. So that's just kind of increasing the risk factor there. And when we also had some other high sources from our high stocking density in those K5, K6 pastures, which is kind of in that dark navy in comparison to some transition paddocks and the summer ones as well. And so when we add these together, we do end up seeing pretty high losses. So in this first graph, we're looking at phosphorus yield in pounds per acre. And so this is we can see we had the most losses in that outwintering pasture in comparison to those transition pastures and also the summer area. So losses were at about 4.5 pounds. And just to kind of situate this data, there's a pretty popular saying that goes about 1 pound of phosphorus is equal to 500 pounds of algae. Well, it's actually a lot more complicated than that when you're considering, temperature and lake mixing and all the conditions need to be right. 4.5 pounds is still pretty high, and it's definitely something we would want to be managing for. This graph also shows us that the majority of those losses were happening during that frozen time period, which is depicted in kind of that light pink. This graph is also looking at phosphorus, but just from the K5 pasture, and it shows us that those losses were really peaking in that March timeframe, again, where we likely have those pretty saturated soils and high runoff conditions. And then in this final graph, It's also looking at phosphorus yield on the vertical axis. And what this one shows is that the majority of those losses were in the dissolved form. And this is actually true for all of the pastures, but again, we're just seeing the most losses in that outwintering area. So while this is definitely not representative of all grazing in Wisconsin, it just kind of shows us a story that when we add high source conditions with high transport conditions, we can get pretty high losses. And anytime we're adding more source conditions to this equation, or we're kind of increasing the magnitude of those, we can see high losses. So definitely something we want to manage for. So outwintering areas can contribute up to 60% of whole farm losses. And I put this in because just if you're doing great work on 90% of the acres on your farm, you don't want this one area to be kind of outshining what you're doing on all those other acres if you have really good management. So these are really, really critical areas in terms of water quality to be managing for. So some of the ways to reduce P loss risk in outwintering areas is to choose areas with low soil test phosphorus, setback from surface waters and concentrated flow areas. Use a more conservative stocking density if you can, and it's really important to rotate from year to year to avoid buildup. So again, kind of key areas to really maximize that water quality benefit on your farm. So now to just go back to that original question I asked, how do we make the system less leaky? And really to do that, it's important to manage for both source and for transport. And really paying attention to where those high source and high transport conditions overlap, which is often what we see in our outwintering areas. Okay, that's it.